Welcome to today's paper reading. Today's paper is titled, EfficientRAG, Efficient Retriever for Multi-Hop Question Answering. This paper was published on the AR14 preprint by Ziyuan Zhuang and colleagues from Nanjing University and Microsoft. The paper addresses the challenges faced by retrieval-augmented generation, RAG, methods, particularly in handling complex multi-hop queries. Current iterative retrieval methods, while effective, often require multiple calls to large language models, LLMs, which can be inefficient. To tackle this, the authors introduce EfficientRAG, a novel retriever designed for multi-hop question answering. EfficientRAG generates new queries iteratively without necessitating LLM calls at each step, and it filters out irrelevant information to enhance efficiency. Experimental results show that EfficientRAG outperforms existing RAG methods on 3 open-domain multi-hop question-answering datasets. The code for EfficientRAG is publicly available at aka.ms/EfficientRAG. Large language models, LLMs, have demonstrated significant capabilities across various tasks, but they still struggle with domain-specific knowledge and can produce hallucinations. Retrieval-augmented generation (RAG) techniques have been employed to address these issues by retrieving external knowledge. However, traditional one-round RAG methods are insufficient for complex, multi-hop questions that require more information than initially retrieved. This paper introduces EfficientRAG, which leverages the idea that the types of relations in multi-hop questions are limited. By using small models to identify relations and associated entities, EfficientRAG employs a labeler and a filter to iteratively generate new queries and maintain relevant information, thereby enhancing efficiency compared to existing RAG methods. In this empirical study, the capability of LLM-based generators was assessed across 3 settings: direct prompt, oracle chunks, and mixed chunks. The datasets used for testing included HotpotQA, 2WikiMQA, and Musique, with models such as GPT 3.5, GPT 4, and Llama 3-8b. The study found that retrieval settings, both oracle and mixed, generally outperformed direct answering. However, the inclusion of irrelevant chunks posed a challenge to the LLM generator, highlighting the necessity for more precise information retrieval. Additionally, the study examined the impact of query decomposition on retrieval efficiency. One-time decomposition outperformed direct retrieval, while iterative decomposition, specifically EfficientRAG Decompose, demonstrated higher recall efficiency, achieving comparable performance to one-time decomposition with significantly fewer chunks. Figure 1 illustrates the performance of LLM generators, including GPT 3.5, GPT 4, and Llama 3-8b, on the 2WikiMQA dataset under different chunk settings. The settings tested include direct prompt, oracle chunks, and mixed chunks. The results show that both oracle and mixed chunk settings improve performance over direct answering. However, the presence of irrelevant chunks still poses a challenge to the LLM generator, indicating the need for more precise information retrieval. Figure 2 illustrates the recall efficiency of 3 retrieval strategies on the Musique dataset. The x-axis is log-scaled to represent the number of retrieved chunks. Each point on the different lines corresponds to the same number of retrieved chunks. The study highlights the efficiency of EfficientRAG Decompose, which achieves higher recall at a similar number of chunks compared to other methods. The methodology section introduces the EfficientRAG framework, which is designed to enhance the retrieval process in RAG systems. This framework consists of 2 main components, the labeler and tagger, and the filter. Both components function as token-level classifiers, determining whether tokens are relevant or not. The framework operates iteratively, retrieving relevant information and enriching the query until sufficient information is gathered to answer the initial question. Additionally, the section discusses the construction of synthetic training data using large language models, LLMs. This involves multi-hop question decomposition, token labeling, next-hop question filtering, and negative sampling. The training process for EfficientRAG involves using an autoencoder language model to derive token embeddings and fully connected layers to classify chunks as either continuing or terminating the retrieval process. Table 1 provides an overview of the amount of synthesized training data used for different datasets in the EfficientRAG framework. For the HotPotQA dataset, 357,000 instances were synthesized for the labeler and 73,000 for the filter. In the music dataset, the numbers are 93,000 for the labeler and 25,000 for the filter. For the 2WikiMQA dataset, 70,000 instances were synthesized for the labeler and 13,000 for the filter. These figures highlight the scale of data preparation required for training the EfficientRAG components across various datasets. Figure 3 illustrates how the EfficientRAG framework integrates into an iterative retrieval-augmented generation (RAG) system. Initially, EfficientRAG retrieves relevant document chunks from a knowledge base, tagging each chunk as either terminate or continue. Useful tokens like KGOT in the diamond center are annotated from continued chunks. The filter module then processes the combined original question and annotated tokens to form a new query, such as, "How large is diamond center?" This iterative process continues until all chunks are tagged terminate or the maximum iteration limit is reached. Table 2 presents the retrieval performance results across various methods and datasets. EfficientRAG shows high recall scores on HotPotQA and 2WikiMQA datasets, achieving 81.84 and 84.08 respectively. Notably, EfficientRAG retrieves the fewest number of chunks while maintaining comparable recall to other methods. The table highlights the best and second best results with bold and underlined fonts, respectively. Table 3 presents the end-to-end question answering performance across 3 datasets, highlighting the highest and second highest accuracy values. EfficientRAG shows promising high accuracy on HotPotQA and 2WikiMQA, achieving the second highest accuracy on music. These results indicate that EfficientRAG performs comparably to LLM-based baselines, demonstrating its effectiveness in multi-hop question answering tasks. In this section, we evaluate the end-to-end question answering performance of our EfficientRAG model against multiple baselines. The baselines include direct answering without retrieval, naive RAG with top 10 retrieved chunks, and advanced iterative RAG methods. For the implementation, we fine-tuned the EfficientRAG labeler and filter based on DBRTAV3 large, and used Llama 3-8B instruct for the question answering stage. The retriever employed is Contrivum Smarco. The training data was constructed using Llama 3-70B instruct prompts, and the model was trained on 4 NVIDIA A100 GPUs for approximately 10 GPU hours with the Atom W optimizer. In this section, we discussed the retrieval performance of the model using the recall at K metric across different datasets. EfficientRAG achieved high recall scores on the HotPotQA and 2WikiMQA datasets, with values of 81.84 and 84.08, respectively. Additionally, the end-to-end QA performance on the 2WikiMQA dataset using GPT 3.5 Turbo 1106 generator demonstrated state-of-the-art accuracy. Furthermore, an out-of-domain experiment was conducted to test the model's adaptability across datasets. The results indicate that EfficientRAG adapts well to different datasets, showing a high degree of transferability, and even surpassing models trained on the original data in some cases. Table 5 presents the end-to-end question answering performance on the 2WikiMQA dataset using the GPT 3.5 Turbo 1106 generator. The table highlights that EfficientRAG achieves state-of-the-art accuracy in this context, demonstrating its effectiveness in handling complex, multi-hop question answering tasks. This performance underscores the capability of EfficientRAG to leverage advanced generators like GPT 3.5 for enhanced QA outcomes. Table 6 presents the results of out-of-domain experiments conducted on the 2WikiMQA and HotPotQA datasets. The data shows that EfficientRAG, a model trained on one dataset, performs well when tested on another, indicating its ability to adapt to different datasets. This adaptability is highlighted by the EM and F1 scores, which demonstrate that EfficientRAG can achieve high accuracy even when not trained on the specific dataset it is tested on. This transferability is a significant advantage, as it suggests that EfficientRAG does not rely heavily on domain-specific knowledge, making it a versatile tool for multi-hop question retrieval tasks. In this study, the authors introduce EfficientRAG, a novel approach for multi-hop question retrieval. EfficientRAG achieves high recall with a minimal number of retrieved chunks, outperforming traditional retrieval-augmented generation methods. This is particularly evident in complex, multi-hop question answering scenarios. The framework also demonstrates significant inference efficiency, requiring fewer iterations and achieving a 60% to 80% improvement in time efficiency compared to other iterative methods. Despite these strengths, the study acknowledges limitations due to resource constraints and focuses primarily on open domain datasets. The authors also ensure that the datasets used are publicly available and do not contain sensitive content. Table 4 evaluates the efficiency of various RAG paradigms. EfficientRAG demonstrates a speed comparable to direct retrieval methods and is notably 3 times faster than LLM-based baselines. Despite this significant increase in speed, EfficientRAG maintains a similar number of iterations, highlighting its efficiency and effectiveness in comparison to other methods. Thank you for watching.